now that we have the mass spring equations, we can actually predict all the different scenarios that can happen, starting with free vibrations. So consider the equation 2y double prime plus 18y equals 0 with initial position 2 and initial velocity 6 squared of 3. Now, in terms of a mass spring model, this is called undamped spring motion. So undamped because there is no damping constant here. So there's no y prime term, and without forcing. Forcing because the right-hand side is it. So we just have pure motion depending on the spring, and we're just neglect air resistance. Now, I will not completely solve the equations. You can see the details in the lecture notes. What's more important is seeing what the solutions signify. So if you want, I can just do the first step. So the auxiliary equation is 2r squared plus 18 equals 0. So r squared plus 9 equals 0. So r is plus minus 3i, which gives you the solution. Y of t is a cosine of 3t plus b sine of 3t. And then you can use the initial conditions. So you can use y of 0 equals 2 to then get a equals 2, and y prime of 0 is 6 squared of 3 to get b is 2 squared of 3. Again, the details of this are in the notes. And then you get the general solution to cosine of 3t plus 2 squared of 3 sine of 3. More importantly, what do the solutions look like? So if you actually plot the solution, then you may notice, again, maybe this is 2. The solutions, they look sinusoidal. Like they go up and down like that, like a sine wave. So this is y of t. Like a sine or a cosine wave. The solutions look like a sine. Sine, cosine wave. And in fact, we can show this. So here's some optional lingo related to this. So you don't need to memorize this. That's purely for fun. Again, don't stop here. It's really interesting. So optional lingo, first of all, the frequency of the wave is the stuff inside the cosine. So notice we have cosine 3t. So this 3, that's what we call the frequency. Omega equals 3. The 3 in cosine 3t. And then the period like d or dt is, well, think like omega equals 3 is like 3 times. So it makes like 3 revolutions in 2 pi. So the frequency is simply 2 pi over omega, which is 2 pi over 3. So kind of 3 revolutions to make 2 pi. That's one thing. And then the amplitude, how big is the wave? I look very sunny here, but okay. The amplitude sounds like attitude. Is simply, you add those constants a and b, and you just take the square root. So square root of a squared plus b squared, which here is, I believe, square root. We had 2 squared plus 2 square root 3 squared. You could calculate that to be square root of 16, which is 4. So think polar coordinates, like square root of squared. And related to this is what's called the phase shift. Think angle. So this is sometimes called delta. By the way, this is sometimes called big R. And then delta is arctangent of b over a. So if you know polar coordinates, it's arctangent of y over x. So in this case, arctangent of 2 square root of 3 over 2. And that's arctangent of square root of 3. And I always get those confused, but it's pi over 3. And why is all this lingo useful? So this is something you may have learned from pre-calculus, which you probably don't remember, but from pre-calculus, it turns out you can write the solution in terms of one cosine. And write, remember y was 2 cosine of 3t plus 2 square root of 3 sine of 3t. We can write this as a pure cosine, namely r cosine of omega t minus delta. So in this case, 4 cosine of 3t minus pi over 3. Which confirms our guess that if you have no damping and no forcing, then the solution is in fact a pure cosine wave, except with this little shift and this, factor of 3.